Hello everyone, welcome to watch this video. I'm Fenggang from University of Minnesota. In this video, I will introduce Tracklace, an efficient data management for interlaced magnetic recording. This is a joint work with collaborators from University of Minnesota. This is a hard disk drive. On the disk platter, there are data tracks. Over the years, this industry has been developing many new technologies to improve the data density of the hard disk drives. Interlaced Magnetic Recording, or IMR, is one of the most promising ones. In IMR, there are two types of tracks, the top tracks and bottom tracks. Compared with top tracks, the bottom tracks are wider and uses higher laser power. Top tracks are written in between two adjacent bottom tracks. But because top track is narrower, bottom track data is not fully covered, so that it can still be read from the gap. We can see that top tracks can be updated with no problem, but updating bottom tracks, well, will destroy the data of two neighboring top tracks. Let's take a closer look. In this example, if we want to update this bottom track block, we need to first read out the data blocks from two neighboring top tracks, so that after the bottom track is written and top track data is destroyed, we can rewrite the top track data back to avoid data loss. In this case, one write operation becomes 5 I/O operations. In other words, an I/O amplification for 5 times, causing serious performance degradation. So how can we solve this performance issue? One observation is that if the disk is not 100% full, we can leave the top tracks empty. So the bottom track updates will not introduce any extra overhead. State-of-the-art solution is on this direction too. On one of the patents filed by Seagate, the data is allocated in 3 phases, depending on the disk usage. In the first phase, when the usage is below 56% full, the data is allocated to bottom tracks. Then after bottom tracks are used up, the allocation enters the second phase, where every other top tracks are allocated. In this way, during bottom update, only one neighboring top track needs to be protected. Finally, in third phase, data is allocated to the remaining top tracks. We will see that I/O amplification is still serious in high usage, potentially 5 times. This motivates us to design a new data management scheme for IMR, especially in high usage. Here we present our proposed Tracklace data management design for IMR. Tracklace has 5 major design components. This video will cover 3 out of them. First, top buffer. When the IMR drive is not full, the data is allocated to bottom track first. An allocated top track can be utilized as buffer space to temporarily store the bottom writes. We call the top track-based buffering space as top buffer. When the bottom block is to be updated, the data will be redirected to the top buffer. The benefit is that once redirected to the top buffer, subsequent write to that block will not introduce any update overhead because it's already in top track. This top buffer block can accumulate multiple updates before being evacuated back to the bottom track. This can effectively reduce the amortized update overhead of frequently updated bottom blocks. As the disk usage increases, the available top buffer space keeps shrinking, and the benefit of top buffer decreases accordingly. In this case, Tracklace has another technique called block swap, which can further improve the IMR performance when the top buffer space is very limited. Here we define a hot block as a frequently updated block and vice versa. Block swap will progressively swap hot bottom track block with cold top track blocks. So the hot data block can be redistributed to the top tracks, and the updated overhead is reduced. If not regulated, top buffer and the block swap will relocate a bottom track block to a faraway top track, possibly across the whole disk. This causes long sync time and affects the performance. Ideally, a bottom track block should only be relocated to a nearby top track. To deal with this issue, we introduce virtual frame, where the maximum relocation distance is bounded. So, the impact on the sync distance is limited. There are other design components and design details. Please check out our full paper for more details. In the evaluation, because existing disk simulator does not distinguish top and bottom tracks, we developed our own simulator called IMR Sim based on disk sim. We use MRSR trace workload replay to evaluate our scheme. We compare the performance of trackless with Seagate baseline. In left figure, we can see that in low disk usage, both trackless and Seagate baseline perform well, with a low average latency. This is because in low usage, top tracks do not contain any data, so the update has no overhead, and both schemes have a good performance. But as usage increases, trackless starts to outperform the Seagate baseline because the baseline does not have special handling for bottom updates. Yet trackless uses top buffer and block swap to effectively relocate hot bottom blocks to the top tracks. Even in extreme high usage, trackless still brings performance benefit. The right figure shows trackless effectively reduces write amplification, which matches the latency trends in the left figure. In summary, IMR technology increases the disk data density but introduces the updated overhead. We designed trackless to reduce the updated overhead and improve the overall I/O performance for the IMR drives. Evaluation showed that trackless can reduce update overhead and the average latency. Please check out our full paper for more details on design and evaluation. Feel free to contact us via this email address. Thank you.